Alrighty. Alrighty, everybody. Cheers. For any of you that haven't seen me before, my name is Phil. I'm AI lead around here. Quiet, please. Trying to teach you guys something, although you don't have to pay attention if you don't want to. I don't really know. It's been a long day. Anyway, yes, my name is Phil. I'm the AI lead around here, and today we're going to be talking about images and image data. But before we do that, I really do want to ask: is anybody here not on the Discord? Okay, good. Thank God. If you are on the Discord, the link for the notebook via Colab is there, also via GitHub. If you feel free, if you want to run it on your own computer, you can do both. It's not anything that's super hardcore. I will say this: if you don't have a Linux or Unix machine, if you don't have anything that can perform a wget command, then then you should probably run it through Colab. And if you don't know what a wget command is, then please run it through Colab, because otherwise it's just not going to work, and that's just going to be a pain. But anyway, moving on. So, image data. Well, first things first. Can this please, for God's sakes, nothing works with me. First things first, what is an image, right? Like, so we all know what an image is in terms of like conceptually, kind of, but like, how would we formally define an image? Does anyone have an inkling of how? Any takers? Yeah, what's up?
Probably like a 2D array of pixels.
Okay, yeah, 2D array of pixels, that's mostly it. Yeah, no need to continue from there, but yeah, mostly a 2D array of pixels, right? I'm going to be a little more mathematical in my terminology, partially because I'm a math major and I like that, and partially because it makes more sense in talking about like images on a high level, but understand that when I say something like, okay, it's going to be coded as a matrix, it's basically a 2D array of pixels, as the guy said. So in terms of they're formally what's called a tensor, and a tensor is a mathematical object, which I don't fully understand, but it's essentially, you can think of it as a matrix with higher dimensions. Now, in terms of for all intents and purposes, we can just think of it as a matrix, or for the more computer science minded among you, just think of it as an array, 2D or n-dimensional array, honestly, because you can have different things. And this representation of images allows you to easily, perform a lot of different transformations to them. If you remember from Math 240, you probably went over like rotation matrices and stuff like that. Well, if you have any sort of linear transformation matrix, you're able to multiply an image by that, and thus be able to rotate and translate and all the fun stuff you ever wanted to do to an image. So to drive that point home, I went and took the identity matrix and put it into an image. And as you can see here, it's basically, wherever a pixel's colored in, you want to put in a 1, otherwise you put in a 0. And there's a lot of different, how do I put this? There's better ways of doing this. So like Grayscale, if you guys have definitely heard of Grayscale, is like, it's instead of just going from 0 to 1, where it's like 0 is like fully black and 1 is fully white, you go in a sort of spectrum. So you've got like n shades of gray between like 0 and 1. Or usually they scale it from 0 to 255 because integers are nicer to use. And there's a whole bunch of different ways of coloring things. But point stands that in the end, an image is essentially just a giant matrix. So with that said, how would we deal with color, right? So what would you guys think? How would you deal with color values at each pixel? Not just, and you'll have things that aren't just like gray and white. You'll have multiple different colors. So how would you deal with that? Yeah.
Like 3 values.
Yep. That's the way you do it. So this is where instead of a simple matrix, you hold a vector of R, G, and B values for each pixel. And this is where the whole idea of using a tensor actually comes in, because a matrix, as you guys know from Math 240, is simply just it's just real number. Well, not necessarily real numbers, but it is just scalars in each column or in each cell. Whereas a tensor allows you to have like a vector at each cell, for example, and that allows some sort of like mathematical understanding of how we'd actually be doing these operations. I'm not going to go into the maths, partially because I don't understand tensors too well, guys. But, if you want to take some graduate level math course, you'll probably be able to figure that one out. But in general, the idea of tensors is where it helps us with the higher dimensionality. That's why Google has the whole thing called TensorFlow, because they're not necessarily just dealing with simple matrices, they're dealing with tensors, which are like generalized versions of those, basically. But in terms of each color, now we can represent it as 3 different values, as you said, but there's a lot of different ways to represent color, actually. And some of them can be a little bit of a pain, some of them not, but in the end, there's a bunch of different ways. And each different way is termed as a color space. So whenever I say like, we'll be changing color spaces. That means, oh, we're representing colors instead of we're doing it this way, we'll be changing into this version of representing colors. And you'll be seeing that later in the notebook, but this is, essentially that's what changing color spaces are. And often these as I said earlier and just now, often conversions between these color spaces are necessary. Can anybody think of why that would be possible or why that would be true? Like, why would I need to bother about converting between color spaces? Yeah.
I mean, one of the programs here was designed to have BRG instead of RGB for absolutely no reason. So that's why I want for two color spaces.
Okay, yeah. Opencv is a pain in the ass, but I mean, like realistically, not just, oh yeah, because we can kind of deal. Like, can anyone think of like a real task in which changing color spaces would actually make things somewhat easier? If not, it's fine. I'm just gonna move on because you'll see that in the notebook, but yep. All right, cool. We will leave this as a surprise for later. So a couple of different color spaces here. The two on the top are honestly the ones that you'll care about the most. RGB, I'm pretty sure all of us are familiar with. We represent things on 3 different axes, how red it is, how blue it is, and how green it is. And each like region is like, you section off a different part of it. HSV is a different one, but it comes up a lot. Instead of representing things as a cube with 3 different axes, you represent it as a cylinder. And so the closer you go in, the less saturated the color is, which means the more like white it is because there's less like actual pigment in it. And then the farther out you go, the more saturated it is. And then as you go up and down, it changes value. So that means you go from super, super bright to at the bottom, which is completely dark, so black. And then as you go around the circle, around the cylinder, each different angle corresponds to a completely different shade. So there's 360 degrees. For the sake of Opencv, we'll be using 180 because to make things efficient, they decided to divide by 2. Don't ask me why, they're stupid. But HSV allows you to represent things not just as like, in terms of RGB values, but just as an angle. And then you can represent the brightness and the saturation of the color in a different way. And we'll see why this is important later because it actually helps you to much more easily pinpoint exactly what kind of colors you're looking for versus RGB, where it's kind of a pain unless you go into Photoshop and start using color pickers and stuff like that. The other one I put down the middle, it's called Scilab, kind of just there as just because I can. Who the heck is joining my screen? Whatever. I'm not even bothered. Who cares? But like, Scilab it's a kind of esoteric. The only reason I put it up there is because I had experience using it once in terms of a research paper that I worked on. But it's there, and it's something that you're supposed to use. Apparently, it's supposed to make some sort of more uniform distribution of the colors, but frankly, who cares? So, moving on. How are we going to implement all of these? Well, as many of you can see from the notebook, we're going to be using Opencv. Now, Opencv stands for Open Source Computer Vision. So fun story. That means that any one of you, if you feel so inclined and have the urge to write C++, in which case, God help you if you feel like doing that, but whatever. If you want to, you can actually contribute to the development of Opencv and start writing code for different functions and bug fixes and stuff like that because it's an open source project. You don't want to do that. Trust me, it's a pain in the ass. But for our intents and purposes, we're just going to be using it blindly. So you can just pip install the program. The command is there. Also, you can just find it if it's the first link on Google. And I would just like to mention that, like, obviously today, I'm not going to be taking you through the entirety of Opencv. They do anything. Like the library has anything from just simple color masking all the way down to like facial recognition models just built into the image library. But I will say that we are going to be doing a project. I'm pretty sure you guys have heard about that later in this semester. It's going to be some sort of image-based task. So knowing Opencv and being able to actually like play with it a little bit is pretty valuable when it comes to working on those types of things. So I highly encourage you guys to, whenever this is over, if you have time between whatever midterms you're forced to take, go ahead and just play around with the library. But with that said, onto the notebook. I can click on that. And while I'm going there, I guess I'll take questions from anyone in chat. Nobody from chat, unless if anyone has a question, I don't know, like ping me or let me know or something like that. But moving swiftly along. Well, Jesus. Stop doing that. There we are. Windows 11 is weird. So, in terms of what? Google, trust me, if it's authored by you, I don't want to run it. it's going to steal my data in some way. Jesus Christ. Okay, yeah. So we're obviously going to be starting with the notebook. Now, first things first, we're going to start like really stupid simple again. Also, actually, I just realized, can you guys read this? Like, is it legible? No, that's great. Lovely. Is it legible now?
Yeah.
All right, bet. What is this line on my screen? Undo. Clear. No. What the heck? Yeah, don't worry about it. Oh, yay, that worked. Thank you for the recommendation. I hate Zoom. You know, for being a CS major, I'm very bad with computers, but we're moving along. So anyway, first things first, we need to import Opencv. Again, pip install command is there. I will say that it is kind of hit or miss whether or not Colab actually has the library in it, so that's why I included the pip install. When I started using Colab, they didn't actually have it, which was a pain, but I think they have it now. So, you know, probably a little redundant to do that. Yeah, as you can see, requirement already satisfied, so a little redundant to do it, but you know what, it's whatever. Another thing I do want to note is that Opencv is annoying because the import name is not the name of the library, unlike NumPy or Pandas or anything like that. Opencv decides to import with CV2. On one hand, yeah, it's nice because it shortens things without you having to import it as CV2. On the other hand, it's a pain because then you forget what the abbreviation is half the time. But something you got to deal with. Now, next up, this is why I said if you guys don't have a Linux, or I don't know if Mac has wget, but if you don't have a Linux system, just like please run this on Colab. This is how we're getting the image. Totally didn't find this on Pinterest at like 12 a.m. But the wget is just the cleanest way I could do it, so that we didn't have the kerfuffle of last time where we had to send out the file and all that stuff. So just need to run this cell, and you'll be able to get the image through a bunch of different stuff. Now, in terms of using the image, first things first, we want to actually look at it, right? So let's plot the thing. Actually, before we plot it, we need to read it, right? So as we mentioned earlier, the image will be read in as a NumPy array. And I can show you that because we'll be using cv2.imread. Imread is the reading function. And then when you hit Shift Enter and you read it in, you'll see that in fact, it reads it in as a NumPy array. That's the pain in the ass in terms of output. Frankly, you don't want to print the direct NumPy array because honestly, usually these images are really large. But just there for proof of concept, it's a NumPy array. And also another key point that I do want to harp on is that Opencv, in order to be optimized, makes sure that every single number that you give it is a 8-bit integer or 8-bit unsigned integer. If you do not use an 8-bit unsigned integer, sometimes it'll actually error out, which is helpful. And it'll tell you like, oh, okay, this is not the right kind of thing. I can't use this. Other times it'll just have some weird, unpredictable behavior that you don't expect. And honestly, those types of things are the worst because I had that happen in like a project I was working on. And you get values that you're not expecting, but you don't know why. And obviously your code is completely correct and there's no logical errors. It's just, small little like bit difference because you're using Python, but Opencv is written in C where they actually care about how large each number is. So I would like to reiterate that whenever you're doing anything with Opencv, just make sure that your image is composed only of 8-bit unsigned integers. If it's not composed of 8-bit unsigned integers, NumPy has a quick thing. If you just do np.uint8 and then put it around whatever the heck you're using, it will force it into 8-bit unsigned integers. Use that. Just make sure to check yourself when you do that. Otherwise, you can have a whole host of different weird problems that are really hard to debug. But moving past that, let's see what the image looks like. I wrote the most inefficient display function ever. But as you guys can see, we have this really weird looking image. If anyone can actually figure out the source of this, then you're honestly the coolest person ever. But in terms of the image, as you can see, it's really weird. And like, on one hand, yeah, sure, one could think that, okay, maybe these are the colors intended, but they look really inverted and they just don't make sense, right? Now, that's because, as one of you said earlier, Opencv treats things as BGR instead of RGB. As we said earlier as well, nobody has a clue as to why they decided to do that. Honestly, I think it's something to do with optimizations, but like, given that it's 3 integers versus 3 integers, I don't see why anybody cares, frankly. Yeah, what's up?
I actually looked it up. It wasn't because of optimization. It's just because that was what was popular at the time.
Okay, well, that time deserves to get burned. I don't know, like,
Exactly.
yeah. All right. Using it as BGR is a pain. And the reason it's a pain is because you'll be expecting something. And then when you print it out to display the image, you'll get this mess. And I mean, it's not a mess, but you'll get this something that looks like this. And you don't want something that looks like this, obviously. So first things first, that's going to show us how we convert between color spaces in Opencv. It's simply the cv2.cvt color with image is the first thing. And then the next thing is the flag that tells it what kind of color space to convert to. All of these will follow the similar format of cv2.color, all caps, underscore, whatever. And if anyone's wondering why it's all in camel case, then I would just like to mention that again, it's because Opencv is actually written in C and all the Python stuff is just kind of a wrapper around C functions. So when everything's written there, it's actually trying to mimic C. It's not trying to do anything Python. Also, aside to that, if you use camel case in Python, please don't. Like, unless the style guide says so for like class names and stuff, variable names and method names and all that, underscores, please, like for God's sakes, use that because I actually have to deal with that in my CMS F2021 class where they use camel case instead of underscores. And it's a pain because not only does it break Python syntax, when you open it up in VS Code, if you have any decent formatter, it'll start screaming at you about your variable names. And then you're like, okay, I don't want to deal with this right now. But yeah, moving on from that, when we display the image in T-38 years, we'll get this thing here. Now that just looks much better, doesn't it? The table's actually brown instead of whatever weird color of under the ocean it was. And this actually seems to like make some sort of sense in terms of what sort of like image we'd be expecting. So from there, and yeah, as I said, if you know the source, you are a true human of culture. But yeah, moving on. Now, we're going to move on to color-based segmentation or color thresholding or color masking or 58 million different names, but you know, it doesn't really matter. It's all the same thing. Now, we're going to try first to, so the whole end goal of this notebook is going to be trying to be able to draw a boundary and identify where the giant gemstone is in the middle. Now, for us, that's really simple, but for a computer, it doesn't really know what a gemstone is, much less, you know, any of that stuff. Now, you could obviously train some sort of ML model. This is kind of a little bit of a flash forward into the future. You can do a bunch of different stuff in order to identify the gemstone in the middle. But the goal of Opencv is to try and do this without having to go into any sort of super high, super like high level data science or super high level AI, anything like that. We're just simply going to be thresholding by simply going to be doing very simple operations image wise, and we'll be able to create a near perfect boundary around this gemstone. So first things first, as we can see, this thing is very green. The rest of the image is very not green. So we're going to be trying to mask out the image. Now, here's where the HSV color space actually comes in really handy, right? Now, as I mentioned earlier, also what the heck? Okay, start menu Y. As I mentioned earlier, there are multiple different color spaces, and HSV can often be really, really useful in this case. The reason that HSV can be useful, if I go back to I hit F12, I hit F12. Zoom out of my way. The reason that HSV can be useful is if I go back to the color space here, right? Sorry, I'm bad. If I go back to the color space here, right? In terms of RGB, we're going to have to be trying to segregate out a bit up in the top, like that top corner over there, right? Now, if any of you know like the boundaries of like that area, then I don't know why you have it memorized, but without going into Photoshop or without like, you know, doing anything like that, trying to like approximate those or like guess and check them can be an extraordinarily high level of pain. And also like depending on the colors you're using, it can sometimes just be annoying. Now, in HSV on the other hand, it's really simple because basically we're just cutting out a slice of cake and we're saying, hey, anything within this, we want that, other than that, get it out of here. And it's more complex than that. We're not necessarily just cutting out a slice of cake. It's more like poking like a triangle and like taking a pyramid out of the side of it. But as you can see, all we need to do is we basically need to find like the maximum angle. So like the highest angle in which, you know, we want the colors to be in, and then the lowest angle. So we get like some sort of arc. And then we just cut out that slice of the color space and say, hey, anything that's within this slice, we want to keep that. Anything outside of that, we want to segment it out. So moving back to the Python notebook, that's why we want to, God, I don't want to look at JavaScript. Go away. Cool, thank you. I did it again. That's why we want to be converting to HSV here, because it allows us to much more easily guesstimate, basically, where these values will be. Now, I had the benefit of foresight, also known as I made this earlier. So I knew that the values that would work would be somewhere between 100, 120 and 250. In reality, you can do the same thing where you like go into like a color picker and you figure out like which one's which and all of that stuff. Honestly, I was good enough with just guessing and checking. So you just start throwing in values and you see like, okay, what sort of colors, if I go between like 0 and like 30, for example, what sort of colors are we taking out? If I go between whatever and whatever, what are we taking out? And stuff like that. And so for me, I went between, what I did is I actually opened the image. I grabbed like the middle pixel because as you guys can see, that's obviously some kind of green that we want. I think it had a value of like 138 or something like that. And so I'm like, okay, cool. So let's try like something between 130 and 150. I'm like, okay, cool. We can keep expanding and expanding and expanding. And basically you're just making a larger and larger section of the HSV cylinder to be the colors that you want. And then anything outside of that, again, you're masking out. So that's what we're doing here. I basically set the color min and the color max as 120, 00, which is 120 and no saturation, lowest value. So it's basically just black at the bottom of that, that angle. And then you have 250, 255, 255, which means the top most with the most saturation. So we're basically going from like if you can think of it, conceptualize it in 3D, we're starting at 120, 00 on like the cylinder, and then we're tracing a diagonal line all the way up to the other section. So then anything that's sort of crossed by that diagonal line and within the slice that contains that diagonal line, we're going to be cutting out of the color space, or we're going to be cutting out of the image. Sorry, any pixel with values in that range. And so CV2 has some nice little functions for that. We have mask, or we have the mask, which we're creating right here, where we use the in range function. And what it does is it takes our image and it finds any values within the range of Cmin to Cmax. And what this mask is it's essentially a binary. It's essentially a binary array. It's 0 where it's where it's outside of the range, and it's 1 where it's within the range, right? So then what you can do is you can go over each little cell of the array, and you can do a quick bitwise AND. So basically, you AND it with the element of the mask, and you go, okay. So if this and the mask, so if you guys remember from Boolean algebra, something and 0 equals 0, and then something and 1 equals something, right? So if you AND it with 0, you're going to get 0, which means that, okay, it's just going to take it out of the pixel and it's going to replace, take it out of the image and replace it with black. If you AND it with 1, then it's just going to leave the color as is. And so what you can see after I run these two cells is that while it's not the greatest, it's extraordinarily noisy and kind of a pain. We have more or less segmented out the gemstone from the middle, minus a few little imperfections. Hooray. But this helps us for moving on to the next part, which is edge detection. Now, as I said earlier, we're trying to draw a boundary around the gemstone, right? So now that we have an image where the gemstone has been taken out, let's go and try to find where the edges of the gemstone are. Now, we can do that with this image. I don't want to say that you have to do the color segmentation in order to do that. You can try it with this image. The difference is when you actually go ahead and do this color mask first, it makes things a lot less noisy. You're not dealing with this very variable environment. It's either something of this color or it's completely black. And so the edges are extraordinarily apparent as opposed to in this one where, you know, we can see it, but for a computer, it can be kind of a pain, especially because at certain points, the colors are very similar. And also it's gold and green and yellow and green are pretty close on RGB, I'm pretty sure. So what we do then is first, we need to try some sort of edge detection thing. Edge detection, there's a variety of different algorithms out there. We're going to be using something called canny edge detection. If anyone wants me to explain the math on it, I'm not going to. I don't fully understand it. It involves gradients, and I just learned how painful gradients are in Math 411 today. So I really don't want to deal with that. But point stands that it's a very, very, very popular and very, very, very useful edge detection mechanism. And so what we're going to do is we're going to apply it, and we're going to be able to figure out where the edges are and ultimately get the outside of that gemstone. But first, we need to apply a blur. Now, blurring an image, if you guys, I mean, you guys know what blurred image looks like, but basically, blurring an image allows it to be more smooth. So instead, I'll run the output so you guys can see. Instead of these harsh transitions that we have right here, the bottom is going to be the original image. When you run a blur, it smooths it out a lot more so that there's a lot less variability in the color. Now, that variability in the color is actually a problem when you're trying to detect edges, because variability in color is how we figure out where an edge is. So when we try to smooth that out and when we try to reduce it, it's much easier for us to pick out where the actual edges are. Now, I will say, there's the kernel size of 51 here. Also, median blur is the one I use. There's a bunch of different types. A lot of people use Gaussian blur. The median blur just worked best here, so I went with that. But again, this is part of the thing of play around with Opencv. There's a million different blurring algorithms. Go ahead and look into which one like works best for your application. But with that said, I used a median blur of size 51 here. Usually people use it of size 5 to 15. So you don't need to go this high. Basically, because it's just a giant green gemstone, I felt like, hey, what the heck? Why not just like exaggerate the effect? So I went with the size of 51. But you can see that like if I go with like 5, it's not as blurred, but it does a little bit. Although again, it's not as apparent, but you can kind of see it in the way that like the colors sort of transition with each other. But given that we have a very, very, very homogeneous image in terms of color-wise, just going with 51 is fine. And also, fun thing is that because of the way the median blur works, it kind of takes the median of like a group of pixels in a certain kernel size. What it does is it helps to, cover over these small little gaps right here, because it looks at that as like, okay, cool, we can just like smooth it over. So now that we've done with that, we can go with edge detection. Now, again, it's another one of those algorithms where playing with the numbers is kind of a pain. As I mentioned earlier, the edge detection algorithm involves finding the gradient of the image at a certain point. I really don't know how to explain that in a nice way because I don't fully understand it. But point stands that like the zero is the minimum gradient and the 50 is the maximum gradient. And honestly, you find those numbers by trial and error. I found them by having the benefit of foresight, but again, usually you can end up with just figuring this out from playing around with your data a bit, and then eventually you'll be like, oh, okay, cool, these ranges work. I do not like my new computer equals, I have to disable all of those again, damn it. So anyway, moving swiftly on, we go down to running this cell, and as we can see, it did get the edges, but also got a lot of the stuff inside. Now, I blame Kyoto Animation for this. They have way too high detailed gemstones, and I don't know about any of you, but I've never seen a gemstone this detailed. So it starts thinking that, hey, all of these different color transitions are different edges. So this is obviously a problem, right? We found the boundary. You can see the external boundary is what we're looking for. But we also have all of this noise in the middle, and we don't want all of that noise in the middle. So how do we go about doing that? How do we go about figuring out where the actual boundary is? Well, we'll go about that with contour detection. Now, a contour, I will say that Google has a bunch of weird, I couldn't really find like a consensus definition. Partially because Google, like when I Googled it, there is a consensus definition, but then Opencv treats it a little differently because like semantics and math. But for all intents and purposes, a contour is essentially a closed curve. So an edge you can think of as just like, a boundary between two things. A contour is one of those that's closed. So if you draw a box around a square, that's a contour. But if you draw a line between like two different kinds of colors, that's not closed, right? There's nothing that like closes it. So that's not closed, there's nothing that closes it. Don't worry about the analogy. But if you draw a line between two things, that's not a contour, that's simply an edge. So what we're going to be doing is contour detection. We're going to be trying to find the closed curves here. Now, the find contours method has a couple of different arguments, which are a little opaque on first glance, but I'll do my best to go through them. First things first, we have, obviously you want to pass in like the stuff, the edges that you found, right? And again, I can mention, it doesn't need to be like an array of edges. Or it doesn't need to be like the edges that you found. You can give it a normal image and it will try to find the contours there. But again, because of all the noise that comes from just regular images, having all of these transformations being applied first and then finding the edges, it's much easier for it to find the contour, but it's much easier for it to find that boundary that we're looking for when we use the picture of the edges versus using just the normal image. So we start with passing it in the edges. Then next thing is this flag cv2.render external. That just means retrieve the, oh my gosh. Sorry, 1 second, I'm gonna correct the typo real quick. You guys are just gonna pretend you never saw it. Where is it? Yeah, all right, cool. No typos wherever found it. Anyway, so first things first is the, it's called the mode parameter. basically what it does is when it finds all the contours, it'll send you back certain types. You can do, there are a bunch of different flags for it. You guys can look those up on your own time because frankly, can't be bothered to deal with all of them right now. But the ones that we're most concerned about is rudder external. And the reason that we're bothered about the external one is because we want to find the external contours. We want to find boundaries that separate parts of the image from the outside world. We don't want to find things that are just like small in the middle of there, like all the noise that's in the middle here. We want to find that outside external boundary. And so that's why we're using that flag here, because we want to find the external contours. The next one is an approximation one. I don't know how the approximation method works, but basically I assume it does something that like speeds up the computation time by assuming like a linear curve instead of the exact curve or whatever the heck, I don't know. But basically I just did none. You can probably play around with it. And if you're using a large task, if you have a super large task, it may actually help you, but never had to deal with that. So I just went with no approximations because it will be exact, damn it. So we take the image, we find the contours, we also find the hierarchy. Now this hierarchy thing I read up on and I'm still not fully sure as to how everything works. But essentially it's some sort of metric of what type of contour you have. For all intents and purposes, the retrieve external contours flag that we have here will basically make that null and void because one of the types of contours is obviously an external contour, and we are only interested in the external contours. So that hierarchy thing is whatever. I just have it there so that you guys know what kind of stuff it returns. But we then can take the image, I'm copying it so that we don't draw over the original one, and then we can draw the contours on it so we can take a look. And as you guys can see, or if you've had it already, boom, we did it. We found the boundary around the gemstone. And thus you can proceed with whatever. This method actually works really nicely because then you can, without the use of any super intensive deep learning model or anything like that, you can simply just segment out a giant part of the image and then use it for like, say if you're like, analyzing, if you're analyzing like jewelry or something like that, you can like segment out where the diamond is, and then you can use it for like analyzing like diamond quality or stuff like that, or a bunch of different things. But point stands, it's really nice that we're able to do this without having to go through all of the messy linear algebra and all of the super high level or super expensive compute power that deep learning requires. Because